So welcome to this video. In this video I'm going to prove formally a formula in propositional logic with a Hilbert style proof. And the formula that we're going to prove, hopefully you've seen it from the title of the video, is alpha implies not alpha implies not alpha. So this formula is a tautology, and we can prove that very simply with a truth table, and then what we're then going to spend much more time doing is proving it without the truth table, proving it with a Hilbert style proof. So if we think about the two different values that alpha can take, now alpha isn't necessarily a propositional variable, it could be a formula itself with potentially multiple propositional variables in. However, that doesn't actually matter. For all of those different combinations of true and false, for all of the propositional variables that it potentially contains within it, its value will always come out true or false, and then the value of this formula is then going to only be determined by whether alpha came out as true or false from the true-false combination of the potentially, n propositional variables that were part of it. So we don't actually need to know more information about alpha in this case, because it's going to come out as a tautology anyway. So whether alpha is true or false, it's always going to come out as true in this case. If it weren't a tautology, if it weren't the case that for whatever true or false values, whether alpha is true or false, this is going to come out as true. If it weren't that case, then we would need to know more about what alpha consisted of. Because, for example, if alpha was a tautology itself, i.e. no matter what combination of true and false you ascribe to the propositional variables that make it up, it's always going to come out true, then it wouldn't matter that this statement, if alpha was false, comes out as false, because alpha is never going to come out as false. So we'd only have to look at the true case, and then if the true case came out as true, then it would overall be a tautology. But in this case, it's going to come out true for both values of alpha, so we don't need to worry about what alpha is made up of to establish whether this thing is a tautology or not. So for the two different values of alpha then, true or false, not alpha can then write nice and easily. So for alpha being true, not alpha will be false. For alpha being false, not alpha will be true. And then we can think about alpha implies not alpha. What's the value of that going to be? So when alpha is true, not alpha is false. So the implication is then wrong, because it's not true to say that when this one's true, this one is true. So it's false in that situation. But for the second one, remember ex falso quodlibet, from false follows anything. So because alpha is false, it's fine that this one is true. It is a true implication in that case, because this implication says if this one is true, this one is true. Because this one was false, it has nothing to say about it, so it's vacuously true in that case. That's something that you have to get used to when you first see logic, but the more you see of it, you realise that it's the best way to define implication, the way implication works. And then let's go further. So alpha implies not alpha implies not alpha then. So the whole thing, and we're hoping this is going to come out as a tautology. So in this line then, so this one is false, so we've got false here, so then we don't need to even go any further, because the moment you have false in the antecedent of an implication, we know that that's going to come out as true, so the implication is true in that case. Here it's true, but then this one also is true, so we've got true implies true, so it is also true in that case. So we've therefore shown with this truth table that this formula here is a tautology. Excellent. So we now want to do a formal Hilbert style proof. So for this, I should probably concretely tell you what the structure I'm working in is going to be. So we're working in propositional logic, zeroth order logic, and we have a bunch of propositional variables potentially. We don't need to know how many propositional variables. We then are going to only have two logical connectives. So I'm going to get rid of and or. We don't need them, and I'm certainly not going to have biconditional implication. the only symbols I'm going to have are not and implication. So my set of all formulas is going to be everything that is generated from the propositional variables with these two logical connectives. Then, now that I've got that, I need to tell you what my proof system is going to be. So we're going to have a Hilbert proof system, and there are multiple different Hilbert proof systems. The thing that they all have in common is that they have big reliance on logical axioms, and then they usually, in zero for the logic, in propositional logic, they usually only have one rule of inference, and that's in contrast to different types of proof system where they have much more rules of inference. So in Hilbert style proof systems, in propositional logic, you usually only have modus ponens and a bunch of logical axioms. So I'm going to give you 3 logical axioms. They are quite standard, but especially the first 2. Pretty much most Hilbert systems that you see defined in different textbooks always have the first 2 in common. The third one is the one that can change, and sometimes they get rid of it altogether and just have the first 2. But I'm going to define the third one in a certain way, and it's quite a common way that you'll see it defined. So the axioms, really axiom schemes they are, they define a bunch of formulas that we're allowed to use and take as axioms in our proof. And it's all formulas that fall into the form that is specified in these 3 axiom schemes. So the first one is anything of the form A, where A isn't necessarily a propositional variable, it could be a propositional formula. So A implies B implies A. Oh, and just a few warnings about the way this video is going to work. So firstly, this formal proof that I'm going to give of this formula is going to be quite long. It's the proof that I came up with for this formula. I thought about it for a very long time, and I came up with this from looking at other things on the internet to get inspiration. But that comes with a warning, which is that it's long and it might not be the most efficient way to do it. And if it's not, if there is some really simple way to do this, I do apologize. The second warning is that this isn't going to necessarily be a polished performance. So at some places I might go wrong and have to correct myself. If the video is uploaded, don't worry, I do eventually get to the right answer. I wouldn't have uploaded it if eventually I end up with the wrong answer. So I will get to the right answer, but I might have to pause and think if I'm going down the wrong track, and I can see that I'm going down the wrong track. And the other warning was that I'm going to be a bit lax with my brackets. So, strictly speaking, up here we should have had an extra bracket there, and strictly speaking here we should have an extra bracket. Oh, in fact, there should be even more brackets. We should have brackets around the knots here. I'm not going to do that. I'm going to put in enough brackets that the meaning is clear. So I'm going to put brackets where it's really, really important for meaning, but I'm going to drop brackets where there should be some formally, but it doesn't really need them. It's still got a clear meaning without them. So I'll be a bit lax with brackets. So I'm being a bit lax with brackets here. So anything of this form, A implies B implies A, that is axiom 1, or the first axiom scheme in our Hilbert proof system. And again, A and B are not propositional variables, they are formulas. So for example, I could take this whole formula and stick it in there as A. As long as I put the same formula here as here, that falls into the set of things from my well-formed formula set that we're going to have as our axioms in our Hilbert proof system. And as I say, this first axiom scheme, firstly, it covers a lot of different things. There's going to be a whole bunch of things that are now axiomatic formulas, but it's also very standard in Hilbert systems. I think you'll pretty much always see it in any Hilbert system, that first one. And the second one's also quite standard. So it has A implies B implies C this time, and we do need another set of brackets, implies A implies B implies A implies C, and another set of brackets there probably to make it absolutely clear. So this says that if it's true that A implies that B implies C, then it is true that if A implies B, it is true that A implies C. So again, A, B, and C are not necessarily propositional variables rather, they might be propositional formulas. As long as you have the same one here as here and here, and the same one here as here, and the same one here as here, then you can have any propositional formula you like. So anything of that structure is now in our set of axioms as well. So that's a whole bunch of propositional formulas. Indeed, an infinite bunch of propositional formulas is captured by each of these axiom schemes. And then finally, Axiom Three, which, as I say, in different textbooks you'll see it done differently, slightly differently. They're often equivalent, might be different in, some of these Hilbert systems may well actually end up having slightly different properties where they change this axiom. Other ones where they change it slightly, it might end up being equivalent. But this is the one I like. I think it's one of the most commonly used ones. So it is that if not B implies not A, then this implies that A implies B. So it's kind of modus tollens or contraposition backwards. So it says that if not B implies not A is true, then A implies B is true. So again, A and B can be any propositional formulas you like. Any formula that's overall of this form is now an axiom and falls into our set of axioms. So those are the logical axioms in our Hilbert system. We've then got our one rule of inference, which is going to be modus ponens. So one of the most famous laws of logic, one of the most famous rules of inference, probably the most famous rule of inference, made famous, of course, by Socrates, all men are mortal, I am a man, therefore I am mortal. That's modus ponens. So modus ponens is an operation, really, on the set of propositional formulas, except that you can't just combine any two elements together. For loads of combinations of two elements, it's not going to be defined what modus ponens gives you. Doesn't work. But for some specially chosen two elements, it will give an output. So it says that if you have a propositional formula alpha, let's say, I'll go back to Greek, and you have a propositional formula of the form alpha implies, and I should stick to Greek, beta. So that's the one of the things that you are inputting, one of the arguments to your operation has to have the first argument in the antecedent position of an arrow logical connective. So its outermost form has to be that it's an arrow structure, and the antecedent has to be your alpha, and only then will it actually spit out an output. So if you have alpha and you have alpha implies beta, you can get beta from that. And things that are going to be allowed then in our formal proof are we're going to be in our sequence that makes up the proof, we're going to be allowed statements that are axioms, and then we're going to allow things that are obtained from previous things in the sequence by applying modus ponens. So you'll have two things in your sequence previously, where one of them is the alpha and one of them is the alpha implies beta, and then you'll be able to add beta as the next element in your proof sequence by applying your rule of inference, which is modus ponens. And that's how we're going to formally prove things in our system, with the axioms and with this one rule of inference, and we're going to have to create a formal proof sequence. And we're going to try and do that for alpha implies not alpha implies not alpha. The one other thing that we're going to do is kind of a cheat, but it's a wonderful cheat, and we're going to accept that we know the proof of the deduction theorem for this Hilbert system. So this Hilbert system does obey the deduction theorem, and the deduction theorem is highly, highly useful. Apologies, it's getting late. So what does the deduction theorem say? So it says that, one thing that I haven't mentioned, so this is proof from just axioms alone, and in this case, this is a tautology, and we can prove it from just axioms alone. But more generally, of course, when we're proving things, we might have assumptions as well. So we might have a set of assumptions, and when I'm stating the deduction theorem, I should include the possibility that you have a set of assumptions. So if you have a set of assumptions, all that is a set of propositional formulas that you're also going to allow to be used in your proof sequence. So they don't need to be axioms, and they don't need to be obtained from modus ponens, from previous things. You can just use them in your proof sequence. They're your premises in your proof, the things that you accept that are true but which aren't quite axioms. So the deduction theorem says that if a set of premises S with a further premise that I'll just call, and I'm overusing alpha, so we'll use gamma now. So S union gamma, so we put in this other premise, gamma, if that is able to prove, so this is the symbol for is able to prove with our Hilbert style proof, if it's able to prove delta, then if you just have S alone, S is able to prove gamma implies delta. So this is the deduction theorem. Stated, if it's the case that this is true, then this is true. And this is often really, really helpful in doing these formal proofs. It's a cheat, basically. Doing a lot of them without the deduction theorem is really difficult. And we're going to use the deduction theorem here because we've got an arrow statement here. So the way we're going to use this is we're going to say, our set of premises is going to be the empty set. We're not going to have any, but then our gamma here is going to be this thing. We're going to assume alpha implies not alpha as a premise, our one and only premise. And then if we can prove our delta, which will be not alpha, from that premise, and no other premises, just the axioms, then by the deduction theorem we'll be able to conclude that the empty set, i.e. no premises, is able to prove gamma implies delta, which is the statement that we've got here. This is our gamma and this is our delta, so that's how we're going to prove it with the deduction theorem. So let's finally, now that we've got the setup, begin. So as I say, this is what I came up with. It is long and complicated. I really do apologise if there is a much simpler way of doing this. So, as I say, we're going to use the deduction theorem. So we're going to assume as a premise alpha implies not alpha. So I might put that as my first line in our proof. And now I'm going to have to think about what we're going to do next. So I think the next thing I'm going to do is I'm going to use Axiom 3 here. And I'm going to make my A alpha and my B not alpha. So then I have to put the not B up here. So it'll be not alpha. Actually, no, this is not what I want to do. Sorry. As I say, that I did warn you this wouldn't be polished. So what I actually want to get is I want to get this thing as my A, and I want to get B as my not alpha. Because if I was able to get this, then I would be able to apply modus ponens and get not alpha. So I'm going to fill that in. I'll keep it in view. So my B is going to be not alpha. So I was actually right. I do want not alpha here. But then my A is not just alpha. It's not, and then this whole thing here. So not, whoops, alpha implies not alpha. And again, note, alpha isn't necessarily a propositional variable. It might be a whole formula. It doesn't matter, because even if it is a whole formula, all of what I'm doing still applies. Whether it's a propositional variable or some whole formula, all of this argument is still going to apply because of the flexibility of these axiom schemes. So, as I say, the A here is this whole thing. B is not alpha and A is alpha implies not alpha. So that's right. And then this will imply A, which is alpha implies not alpha, implies B, which is not alpha. So this is Axiom 3 that we got that from. So I'm allowed that in my proof sequence. So far I've had a premise as my first line in my proof sequence, and second I've had Axiom 3 as my second line. So the idea is that if I can get this thing now, then I'll be able to apply Modus Ponens. So say I had that, then I'd be able to apply Modus Ponens and I'd get this thing, and then I've got this, so I can then apply Modus Ponens with this and this to get not alpha, and then by the deduction theorem I'd be able to conclude what we want, that no premises, just the axioms is able to prove that alpha implies not alpha. So now my concentration is going on to getting this. How do I get this? So the thing that we're going to aim for, and there's going to be lots of sides to this proof because we're going to need lots of other results, things that can be formally proved. So the way that I'm going to get this is, how am I going to get this? So we're going to write down Axiom 2 next. And the Axiom 2 that I'm going to have is not alpha implies not alpha implies, and I might have to correct this if it goes slightly wrong. So alpha implies not alpha. This is what I think I remember doing. So let me clarify what I'm doing here. So we're using Axiom 2 up here. This thing is A, not alpha is A, B is not alpha, and C is not alpha implies not alpha, so all of that is C. And so I'm going to be able to put this here by Axiom 2. So splitting it up, it goes to not alpha implies not alpha, and that's good. That's something we should easily be able to get from this. We'll need Modus Tollens the right way round, so our Axiom 3 isn't, strictly speaking, Modus Tollens, although I think you can be forgiven for calling it backwards Modus Tollens. But we need to get Modus Tollens the right way round, i.e. A implies B implies not B implies not A, so that from this we will be able to conclude this, but we'll have to prove Modus Tollens, and that'll take a bit of work. But we should be able to get that from this premise. And then we need to finish this, so this implies, and then it's this one implies this one. So not alpha implies not alpha implies not alpha. And that's Axiom 2 there. And the use of this is that if I can now get this thing, then I'll get this here, and there should be, for clarity, another set of brackets around that. I'll get this thing. Then if I can get this, by Modus Ponens, of course, then if I can get this thing, which I've already sort of said I'm going to be able to get, then by Modus Ponens I can get this, and oh look, that is exactly what we want. So what shall we do next? I think before I show you that we can get this, I should show you how we can get this. So this is actually beautiful. This is kind of a side proof. Or should I just put it in the main proof itself? Maybe I will put it just in the main proof and make it all into one. I think that might actually be tidier. So how do we prove something like that? Well, you can prove anything kind of... a nice trick is that you can prove something actually of this form, much more general. I can put in, phi there, where phi is any propositional formula you like. Because what this says is that if not alpha is true, then, well, the moment that not alpha is true, that not alpha is going to be false, because this is not alpha. So this one's going to be false, and therefore it doesn't matter. This implication is immediately going to be true because it's going to be vacuously true. So it is going to be true that when this one is true, this one is true. And then when this one's false, then the whole implication is vacuously true anyway. So this is actually a tautology and something that we're going to be able to prove. So how are we going to prove that? Let me remember how we prove this. So you can put whatever you like there, and we will obviously stick in the thing that we want, which is not alpha implies not alpha. So we're going to start with Axiom 1, I think, and then we're going to invert it with Axiom 3. So I'm going to put not phi in as my b, and then we're going to want not alpha, I think. So I think this is, this is what we want. Not alpha implies, and I will just rub this line out because that's not part of the proof. In fact, I'm going to rub this line out as well, and we will put in our specific thing that we want, but be aware that you could have done this for a general phi. It doesn't have to be this thing specifically. So our next line of the proof is going to be using axiom 1. We're going to have as our A, not alpha, and then as our B, we're going to have not, and then this whole thing. So we're going to have not alpha implies not alpha. And then as our A, we have to have the same thing again, so it'll be not alpha. So does that have enough brackets in? I think that bracket's overkill there, so we'll get rid of this one. So this is, oh, and I put it on the other side, I shouldn't have bothered. Oh no, that one is important. Sorry, I'm getting confused, apologies. So this is axiom 1 here. Next, what are we going to do next? How are we going to conclude not alpha is the problem. So we can definitely get that. Oh, this is why we should have done this as a separate proof. So we're going to have to use the deduction theorem. So apologies. Yeah, no, I can't do this all in one go. We're going to have to prove this side claim as a side claim. So my claim as a side claim, and we'll go back to phi, is that this is something that is provable separately, and then we'll be able to just use it in our proof. So not alpha implies phi, and this is what we want, where phi is going to be not alpha implies not alpha. So this is something that we're going to be able to prove. And the way we're going to prove it is by the deduction theorem. So we're going to take as our premise not alpha. We could try and prove it without the deduction theorem, but God knows how you do it. The deduction theorem helps hugely. So we're going to take not alpha as a premise, and then we're going to prove this part, not alpha implies phi, and then by the deduction theorem then, no premises is able to prove not alpha implies this thing. So we have as our premise not alpha, and then we're going to do what I said, which was use axiom 1. So we'll have not alpha implies, and then we're going to have not phi as our B, and then again as our A, not A. So that's axiom 1. Then we're going to use modus ponens. So we have our premise here. We have this premise appearing in the antecedents of this implication here. So by modus ponens, we then have not phi implies not alpha. That's by modus ponens. And now we're going to use axiom 3. So our B is going to be phi, so we'll have not B, which is not phi, and our A is going to be not alpha, so we'll have not A, which is not alpha, implies, and then A implies B, so not alpha implies phi. And so that's by axiom 3. And then we'll apply modus ponens. Here we've got this, it's here in the antecedent here. So modus ponens with those two gives us then that not alpha implies phi, which is exactly what we wanted. So this is by modus ponens. And then by the deduction theorem then, we have what we wanted, that not alpha implies not alpha implies phi. So this is always provable with no premises, just from the axioms. So what we're now going to do is use the fact that we know that thing is provable here. So we're going to just now stick in not alpha implies not alpha implies not alpha implies not alpha, which we've just proved separately. And now now we can apply modus ponens because we've got the antecedent of this huge great implication here. So we'll then get the consequence just left over. So we'll have not alpha implies not alpha implies not alpha implies not alpha implies not alpha. And that's by modus ponens. So we're getting closer. So we are getting closer, much closer. So if we just take a step back and look at our overall strategy, so if we get this thing now, we'll be able to apply modus ponens and get this thing, and then by modus ponens we will have this thing, and then we can put this premise into here and get from modus ponens this thing, which then means we've got what we wanted. We're aiming for not alpha, remember, and then by the deduction theorem we're then going to conclude that from no premises we would have been able to conclude that alpha implies not alpha implies not alpha. So next I need to convince you that we can have this thing. So this is going to require me to prove modus tollens to you. So this is going to be a separate proof as well. So modus tollens is not a rule of inference in our Hilbert system. It's a rule that is going to be derivable in our Hilbert system as being true, but it's not. It's neither an axiom nor is it a rule of inference or a rule of deduction. So it is that A implies B implies not B implies not A. So a kind of axiom 3, but the right way round is what's called modus tollens. And this is always going to be a tautology, and it's something that's provable in our Hilbert system. And again, A and B aren't necessarily propositional formulas. They aren't necessarily variables. They could be complicated formulas. So how are we going to prove this? So I think the way you prove, we're going to need quite a lot to prove this. We're going to need double negation introduction, double negation elimination, and hypothetical syllogism as well. So we need other rules of logic that are derivable in our Hilbert system, provable in our Hilbert system. So let's start with double negation elimination. So this is the name for the fact that something that is always provable in our Hilbert system is that not alpha implies alpha. So this is another statement like what I've got over here, this one about phi. Where is it? Where did I write it? So like this statement is always provable no matter what alpha and what phi in our Hilbert system. And this one, modus tollens, is always going to be provable. This is another one that's always provable, and it's named as well. It's called double negation, which I've abbreviated down to DN, elimination. So how are we going to prove this? Probably by the deduction theorem as well. Everything is by the deduction theorem. It's so much easier to prove things by the deduction theorem. So we'll take as our premise not alpha, and we're going to derive alpha. And then by the deduction theorem, we'll be able to conclude that with no premises, not alpha implies alpha would be provable. So how are we going to do this? How do you do this? So not alpha, we would then get... Do I remember how to... I might have to pause this to remember how to prove this. Ah yes, I've remembered now. So we firstly apply axiom 1. So not alpha imply... Oh, and I haven't told you what we're doing with axiom 1. So we're putting not alpha as A. And then as B, I think we put not alpha as B. And then, of course, implies A, so not alpha. So that's by axiom 1. Another bracket there. And then modus ponens, we have our premise here. Here's the antecedent. So by modus ponens, we then get that not alpha, 4 nots, implies not alpha. So that's by modus ponens. And now we're going to apply axiom 3 twice. So axiom 3 with this thing that we've just derived as our antecedent in the implication. So this will imply, so this bit here is our B and this bit here is our A. So A is going to become not alpha, or A is not alpha, and B is not alpha. So then we've got this, here it is in the antecedent, so I should just write that that's by Axiom 3. So by Modus Ponens we then have that not alpha implies not alpha. And now we're just going to apply Axiom 3 again. So not alpha implies not alpha. It's true by axiom scheme 3 that this implies not alpha implies alpha. So that's again axiom 3, where this time A is not alpha and B is alpha. And then we've got not B and not alpha, and not A here. Modus Ponens again, because this obviously is the same as this. So we'll then get not alpha implies alpha, and excellent. We have not alpha as a premise, so again by Modus Ponens we then get alpha. And hence then by the deduction theorem we're able to conclude that from just axioms we would be able to get not alpha implies alpha. So that's how you prove double negation elimination in this Hilbert system. Now double negation introduction, which is the opposite thing. It's that it's always true that alpha implies not alpha. And this one I believe you just apply double negation elimination and then apply axiom 3. So we're going to use double negation elimination on not alpha. So we're going to have not alpha implies not alpha. So you see I'm just using here double negation elimination, but instead of putting in alpha to double negation elimination and having not alpha implies alpha, I've put not alpha in, and double negation elimination is true no matter what alpha you put there, so I can put in particular not alpha. So this is true by double negation elimination. And now I think I can just use axiom 3 to fix this. So this is one that we don't actually need the deduction theorem for. So by axiom 3, not alpha implies not alpha implies alpha implies not alpha. That's something of the form axiom 3, and then of course modus ponens now to get alpha implies not alpha. And then I'm done. That's what I wanted. I've proven this. So there's double negation introduction. So those are two nice rules of logic that are provable in this Hilbert system: double negation elimination and double negation introduction. And I'm going to need them. The reason I'm bothering with this is I'm going to need them to prove modus tollens. Right, the final thing I'm going to need for modus tollens is something called HS, which has a fancy name. It's hypothetical. Am I spelling this correctly? Hypothetical syllogism. Apologies if that's spelt wrongly. So this is a really complicated name for something that's really simple. It is that if you have the two premises, so my set of premises is going to contain that it is true that alpha implies B, A implies B and B implies C, then from that it is provable that A implies C. And this is obviously really common sense. You know, if it's true that A being true implies that B is true, and if it's true that when B is true, it implies that C is true, then it is true that the implication that A being true implies that C is true is also true. And the way that we would formally prove it is again by the deduction theorem. Let me just remember how we do this by the deduction theorem. Oh yes, I remember. At least I think I do. Yes. So we would take our set as specified with these two things, these two premises in, and we'd add in another premise, which is A, and then if we can prove from this C, so if this proves C, then by the deduction theorem, S alone would prove A implies C. But doing this is really easy, you know, so we've got A as a premise, we've got A, sorry, yes, we have got A as a premise, we've got A implies B as a premise, so by modus ponens we then have B, but we then also have B implies C as a premise, so by modus ponens we have C, so we've proven C from this set of premises, so by the deduction theorem from just S we would be able to prove A implies C. So that's how you prove hypothetical syllogism. And now I think we can prove finally modus tollens, which is up here. So we want to prove this. How do we do this? So we do it by double negation elimination, double negation introduction, and modus and axiom 3 and hypothetical syllogism. So how do we do this? I'll have a pause just to think about this. So I think by the deduction theorem is again a good idea. So we'll take as our one premise A implies B, and I'll stop writing out premise and axiom 3. It takes too much time. So we'll take this as our one premise, and then if we can derive this thing, then by the deduction theorem this will be true. So we have A implies B, and then by axiom 3, I think, is probably going to be a good idea. So we'll want not A implies not B implies, and then I think by axiom 3 that is then not B implies not A. And this is confusing because of course my B is now in the original way that I wrote my axiom scheme 3 is now not A, and my A is not B. But I think then that all fits out. Yep, so that's axiom 3. So I can have that in my proof. Then I'm going to have that, no, not this actually. I'm going to have B implies not B, which I can have because I've proven double negation introduction in my Hilbert system. So I can have that in my proof because I've now proven that separately. Then by hypothetical syllogism now, I know that A implies not B. And I also know by double negation elimination that not A implies A. So again, by hypothetical syllogism, I should have said here, I'm applying hypothetical syllogism on these two that I've got here, and I've already proven that this is an acceptable, provable law of logic that holds true in my Hilbert system of proof, which is why I'm accepting this argument. So because A implies B and B implies not B, I've then concluded that A implies not B. And similarly here, I'm going to use hypothetical syllogism on this one and this one. So because not A implies A, and then A implies not B, I'm going to conclude then that not A implies not B. So that's by hypothetical syllogism. This is by double negation elimination. This is by double negation introduction. Oh no, that's not by double negation introduction, that's by hypothetical syllogism again. And you get the idea, I won't write more of that out. So now I've got this thing here, which is my antecedent. So then modus ponens, I get not B implies not A, which is what I wanted. So now by the deduction theorem, it's true. This thing is true with no premises. So again, I've proven modus tollens. Right, so all of that was to prove modus tollens. And the reason I wanted to prove modus tollens is now to plug in for A, what am I going to have? I'm going to have alpha. And for B, I'm going to have not alpha. And then my not B is then going to be not alpha. And my not A is going to be just not alpha. So going back up to our proof here. So by modus tollens then, alpha implies not alpha, implies not alpha, implies not alpha. That's by Modus Tollens, MT. Now, because if you remember this bigger proof that we were trying to do here, we had alpha implies not alpha as a premise. So I can do Modus Ponens now on this thing and therefore get not alpha implies not alpha. That's by Modus Ponens. And now, where are we? Now I'm going to do Modus Ponens again because I've got this thing, which is what I wanted for here. So now that means, and I think we're nearly there now. Now that I've got not alpha implies not alpha implies not alpha. So again, that's by Modus Ponens. And then where do we go next? This thing I must stick in somewhere. Over here, this is what I wanted. No, this isn't what I wanted here. This is what I wanted up here. So here is this thing. So by Modus Ponens of this with this, I'll then get this. So we then get alpha implies not alpha implies not alpha by Modus Ponens. And you might think, oh, that's what we wanted to prove. Are we done? No, because remember, we had a premise. In order to do all of our arguments, we needed that premise. So we now do have to finish the deduction theorem. So by Modus Ponens now, because this is our premise, we get not alpha. And hence, with this one premise here, alpha implies not alpha, we were able to derive not alpha, and then by the deduction theorem we are therefore able to conclude that with no premises, alpha implies not alpha. So this thing is provable within this proof system. And we will finish there. As I say, it's a long explanation, and it's made much longer because I did go to the trouble of proving all of the rules of logic that hold true in this proof system that we needed to use in our proof. So I proved double negation introduction, double negation elimination, hypothetical syllogism, and modus tollens. And I also proved another really nice result, which is this one. This is really useful. I mean, this isn't the form you would normally see it in. The sort of more common form to see it in would be alpha implies that not alpha implies anything. We needed it in this form where we had the not alpha here and the not alpha here, but this would be the more common form because obviously when this one's true, this one will be false, and therefore it's true that it implies anything. The same thing holds true here, just slightly more complicated because of the additional not symbols, but the fact all you need is a differing number of not symbols in between the two. Here there's a different number, here there was a different number, and it works. It's something very handy. I think some people do have a name for this, however I don't think it's consistent, people using the name for this, so I don't remember the name for this, but it is a really useful rule of logic that holds true in certainly this Hilbert system, or is provable in this Hilbert system. It's always a tautology in propositional logic, but it's provable in this Hilbert system. So thank you for watching. We will finish there.